There is a region of space where the universe forgot to leave a fingerprint. Between every distant galaxy and every telescope on Earth, there is gas. Thin, cold, almost invisible hydrogen drifting through the empty stretches that separate one galaxy from the next. Light from distant quasars, the brightest objects in the known universe, passes through this gas on its way to us. As it travels, the hydrogen drinks small portions of that light at very specific wavelengths in the ultraviolet, leaving dark notches in the quasar's spectrum. The pattern this creates is called the Lyman alpha forest. It is a dense thicket of absorption lines stretched across the light of nearly every distant quasar ever observed. Each line is a single cloud of intergalactic hydrogen, recorded by the dimming it imposes on light that began its journey billions of years ago. The forest is one of the most reliable maps astronomers have of the matter between galaxies, a record written directly into the light itself. Then there are the gaps. In a small number of quasar spectra, the forest thins where it should be thickest. Whole stretches of wavelength contain no absorption lines, or far fewer than the surrounding regions. The light passes through almost untouched. The dark notches that should be there are simply not there. This is the missing absorption region, a section of the cosmic record where the pen lifted off the page mid-sentence, and the universe never explained why. Under the current understanding of cosmic structure, intergalactic space is not empty. Most of the universe's normal matter, the kind that builds stars, planets, and bodies, is not inside galaxies at all. It is spread thin across the volumes between them, in long filaments and diffuse halos, mostly in the form of hydrogen. The Lyman alpha forest is the direct fingerprint of this gas. Where there is hydrogen along the sightline, there is absorption. Where there is more hydrogen, there is more absorption. So when a quasar's light arrives at our instruments carrying a stretch of spectrum without the expected absorption, the implication is direct. Along that specific line of sight, through that specific span of distance, the hydrogen pattern that should be present is not present. The forest has been pruned. A clean gap in the forest is not subtle. It can extend across redshift intervals that correspond to tens or hundreds of millions of light years of intervening space. For that volume to leave no measurable imprint on the light passing through it, something about its hydrogen has to be very different from the rest of the intergalactic medium. Either there is far less of it than models predict, or the hydrogen that is there has been changed into a form that no longer absorbs at the expected wavelength, or the gas exists but cannot be seen at all in this signature. None of these possibilities is comfortable. Each one removes something the models had assumed was reliable. The universe is supposed to be filling in this map evenly. The gap says it did not. To approach the problem cleanly, the reasoning has to start with what is observed and work outward to what is missing. What is observed is straightforward. A quasar produces a continuous spectrum of light. That light travels for billions of years through intergalactic space. When it arrives, certain wavelengths are darkened by hydrogen absorption at every redshift the light has passed through. In most spectra, the pattern of these darkenings is dense and consistent, with a roughly uniform distribution of intergalactic hydrogen. In some spectra along certain sightlines, the pattern thins. The expected absorption is reduced or absent across a contiguous stretch of wavelength. What is missing is the underlying cause of that thinning. The data tells us that fewer absorbers were encountered along that path. It does not tell us why. Several physically plausible reasons exist. The first is that the hydrogen density along that line of sight is genuinely lower than elsewhere, that the light passed through an unusually empty stretch of the universe, a true void in the intergalactic medium. The second is that hydrogen is present in normal amounts, but it has been ionized, stripped of its electron by some local radiation source. And ionized hydrogen does not produce the Lyman alpha line in the same way. The third is that the absorption is happening at a different wavelength than expected because the gas has different physical conditions than the model assumes. The fourth is that the gap is not in the universe at all, but in the instrument, an artifact of how the spectrum was measured, calibrated, or processed. The problem is that the available evidence cannot cleanly distinguish between these. A single quasar sightline gives a single thin pencil through cosmic volume. The geometry of that pencil cannot be reconstructed from one observation. A void and an ionized region look similar in absorption space. An ionized region and a calibration error can produce similar shapes in the data, and the only way to confirm any of them independently is to find other signals from the same volume, galaxies, emission lines, secondary absorption features that constrain what is actually there. In many of the most pronounced gaps, those secondary signals are not present. The volume is quiet across multiple detection channels. This is where the gap becomes more than a curiosity. It becomes a place where the universe is silent on multiple frequencies at once, in a region where current models predict it should be speaking. The deeper problem is one of inference. Cosmological models do not predict the location of any specific gap. They predict the statistical distribution of intergalactic hydrogen, how much there should be on average, how clustered it should be, how it should evolve over cosmic time. Individual sightlines are expected to vary. A few unusually empty paths through the universe are part of the prediction, but the depth, the size, and the frequency of certain observed gaps push past what the statistical distribution comfortably accommodates. The models do not break here, they strain. Strain is harder to interpret than failure. A clean failure would tell physicists something specific is wrong. Strain only tells them that the data and the theory are not yet at ease with each other. The strain could mean the underlying physics is incomplete, or it could mean the sample of observed quasars is too small to fairly test the prediction, or it could mean the assumptions about how hydrogen ionizes across cosmic history need revision. None of these conclusions can be ruled out from the data currently in hand. The light came in, the absorption was missing, and the universe did not provide a return address. When this is examined closely, what becomes clear is that the gap is not just a hole in the data, it is a hole in the conditions under which the data was supposed to mean something. The Lyman alpha forest works as a measurement tool only because the assumed link between hydrogen presence and absorption strength holds along the sightline. When that link is uncertain, when the same absorption profile could be produced by very different underlying physical conditions, the measurement loses some of its diagnostic power exactly where the anomaly appears. The instrument is fine, the light is fine, the hydrogen physics is fine. The gap is in the chain of inference that connects them. This is the structure of an evidence gap rather than a paradox. Nothing observed contradicts known physics directly. What is missing is the additional information needed to decide which of several known physical processes is responsible. Without that information, the anomaly cannot be assigned to a cause, and without a cause, it cannot be folded into the standard picture of intergalactic structure. There are sharp limits on what can be done about this. A telescope can collect more light from the same quasar, improving the precision of the spectrum. It cannot collect light that traveled along a slightly different path through the same volume. Every quasar provides only one line of sight, and the universe does not offer duplicates. Adjacent quasars sample adjacent volumes, not the same one. The geometry of the cosmos is uncooperative on exactly this question. Some progress has come from looking for the indirect signatures. If a gap is caused by a true underdensity of gas, there should be fewer galaxies in the surrounding volume as well, because the same processes that thin the gas also thin the galaxies. If it is caused by enhanced ionization, there should be a source of ionizing radiation somewhere nearby. If it is caused by an instrumental effect, repeating the observation with a different spectrograph should change the result. Each of these checks has been performed for some of the most studied gaps. The results are not uniform. Some gaps line up with regions where galaxies are also scarce. Others do not. Some appear to be associated with intense radiation environments. Others have no obvious ionizing source within a plausible distance. Some replicate cleanly across independent observations. Others soften or shift when remeasured. There is no consistent pattern. There is only a population of gaps, each of which fails to fit the same explanation as the others. This is the worst kind of evidence gap. Not one missing piece, but a missing framework that would tell us how the existing pieces should be assembled. What remains is a precise list of things current physics cannot do with this anomaly. It cannot identify from a single sightline which of the candidate causes is responsible. It cannot reconstruct the three-dimensional structure of the intervening medium from the one-dimensional spectrum. It cannot independently verify the ionization state of gas that emits no detectable signal. It cannot rule out subtle systematic errors in spectroscopy at the level required to confirm the most extreme gaps. It cannot predict in advance which sightlines will contain a gap and which will not. What it can do is measure the absorption that is there and the absorption that is not. Everything beyond that is inference, and the inference has run out of leverage. The gap continues to be observed in new spectra as more quasars are surveyed. The pattern of the gaps does not stabilize into a clean signal as the sample grows. Each new gap brings its own configuration of associated galaxy density, radiation environment, and instrumental conditions. The phenomenon is reliably present and reliably unresolved. Somewhere along the path that the light took to reach us, the universe did not write what it was supposed to write. The hydrogen that should have darkened the spectrum either was not there, or was changed before the light arrived, or was hidden by something the current models do not yet describe. The missing data is not waiting for a better telescope. It is waiting for a different question.